Rule number one, know what you're going to do before you walk in the lab. Right? You can get away with coming to a lecture class and never touching the chapter before you hear it in class. I wouldn't advise it, but you can do that, and it won't put anybody at risk. But if you walk into the lab and you don't know what you're going to do, then you put yourself and your neighbors at risk. So preparation is number one, rule number one. And I suppose preparation includes preparing for what's going to happen in the lab. Safety precautions, like, are you going to be working with glassware? Like, you need to at least protect your eyes. You're going to be working with hazardous materials like acids or bases. They can splash in your eye. Protect your eyes. Protect your hands. We have gloves, disposable nitrile gloves. No latex in this lab. By the way, is anybody allergic to latex? Maybe you don't even know, because you don't find latex gloves anymore. They just automatically assume that there are enough people that are allergic to latex, they just don't even bother with them. So they use nitrile. Nitrile is good for most things. When I worked in the lab, I preferred trying to think of the right generic term for it. Oh, it's escaped me. I'll think of it later. But you need a lab coat too, right, to protect your clothes, because if you spill something on you, right, if you're wearing the clothes, then you're probably going to want to come out of them. But if you're wearing a lab coat, you can just shed your coat. You don't have to get naked in the middle of the classroom to avoid being burned by something, right? And then you head for the shower too. And the shower's in that corner with eye wash and a first aid kit, and a fire blanket is right here on the side wall. Everybody know how to use a fire blanket out of one of those things? Grab that cord and just start spinning, and it'll come right out and wrap you up and smother the fire. Stop, drop, and roll, right? By the way, if you need to use the shower, be absolutely sure that you do. And you'll know if you need to use it. Because when you pull that handle, that comes out at gallons per second. It's going to drench you for sure and cover the whole place with water, which is better than chemical injuries, of course, right? But be sure that you need it before you do. Let's see. There's a drain in the floor, but that's not big enough to drain the water off really quick. It's not like you're standing in a shower with closed doors. All right. As a general rule, well, as an absolute rule, your legs need to be covered. Right? Your lab coat only goes down to your knees, so be sure your legs are covered and your feet are covered. Right? No sandals or open-toed shoes in the lab when we're doing an experiment. Right? Since we're using this space for lecture and lab, you can wear sandals as you want, but when the lab starts, you got to change shoes. Eating, drinking, smoking, chewing, applying lipstick in the laboratory. Okay, we don't have to worry about that, do we? Lipstick. Besides, you have something, if you have a drink, you can bring it in the lab, and during the lecture, if we're not doing an experiment, since we are using it as dual purpose. But when we start an experiment, bring your drink up here and put it close to mine, because this area, we don't have any chemistry going on in this area. I mean, there's a lot of junk here, but I don't know who left that there. It's been here for 6 years. So, if you need to bring a drink into the lab, keep it up here while we're conducting experiments. Waste materials. I'll usually, for each lab, if we have any chemical waste, I'll have a waste beaker situated somewhere that you pour your waste into. And other materials, say accidental materials like breakage, glass breakage, we have a sharps box over there with a broom and a pan. So if you do have an accident, first thing you do, tell somebody, right? If I'm in the lab, tell me. And then tend to it immediately. If it's a chemical spill, you need to, if it's just on your hands, you can rinse those in the sink. Or if you splash something on your face, we have an eye wash station over there. That puts out a lot of water, but not as much as the shower. And then, of course, if you get covered, you hit the shower. Or if you get a cut, we need to tend to it immediately. How do you deal? Has everybody had first aid in here? First aid class? What do you do with a cut to stop bleeding? First. Direct pressure. Yep. Now that's, of course, unless you have a piece of glass sticking in it. You don't want to direct pressure and drive the glass further. So you have to use a little common sense. If there's a piece of glass in there and it's deep, then you want to just cover it. Don't try to pull it out because it may open up an artery. You know, it could be. I remember first aid class, they always describe these horror stories. The guy who was teaching it was an EMT, and he was on a scene where a person had a piece of metal stuck in their eye. It's about that long. He says, you don't pull that out. You're not qualified. He said, what you do is stabilize it. You put something like a cup over it like that to keep anything from moving it, and then wrap it. And then get them to the emergency room so a surgeon can remove it without doing more damage. Okay. But if it's a clean cut and there's nothing else in it, direct pressure. You only apply a tourniquet if the pressure doesn't work. Now, when I first was trained in first aid, you applied a tourniquet at certain places, like here on the brachial artery or around the leg on the femoral artery for the extremities. And periodically you would loosen it and then retighten it just to let the blood flow back into the, but now I think they say you don't loosen it at all, because if you do, you may not get it stopped again. So you put the tourniquet on it and you get to emergency care quick. Let's see. Cleanliness is next to godliness. Keep your work area clean. And if you're conducting an experiment here, where do your papers go? Over there, right? You don't have papers right next to your work area. You have them separated, right? Especially if we're working with an open flame. And that the first one we're going to do next week, I believe, actually. Yeah, laboratory techniques. I have to hand that one out, don't I? Yeah. We're going to have an open flame. We're going to use a Bunsen burner. So you don't want your papers close to that, right? Right. What temperature does paper catch fire? Anybody know? I know it in Fahrenheit. 451. You ever seen the movie or read the book by Ray Bradbury called Fahrenheit 451? It's a science fiction. Yeah. They had firemen in that movie, but the firemen didn't put fires out. They confiscated books and burned them. Anyway, that's the only reason I know that temperature. Let's see. there's a mention in here of using good judgment. And sometimes good judgment, it develops over time. Right? You know how to be safe around your own house, especially if you have kids. You know how to keep them safe from doing stupid things. So start there, what you know, how not to do stupid things around your house. And then we expand on those for the laboratory because we have different things in the laboratory. If we're dealing with glass, right, be sure of two things. What's the temperature and where are you going to put it, right? If you've never put anything in it before, it's never been near a heat source, then you're pretty safe. You can grab it. But if it's been near a heat source, you want to be sure that it's cool before you grab it, or you have tongs to grab it with. Okay. So there are various ways that you can injure yourself in the laboratory. One is heat, right? One is flying objects. One is caustic materials, those that can cause chemical burns. Now, EPA, I think it's OSHA, defines, they have definitions for caustic materials. And we haven't talked about pH yet, but that's, have you had pH in any of your other classes? It's an expression of acidity, right? The lower the pH value, the more acidic it is. The higher the pH value, the more caustic it is. And in general, anything less than, I think it's 2.5 pH or greater than 10 pH is considered caustic. It can potentially burn your skin or cause eye damage. By the way, pH less than 2.5, stomach acid, right? Stomach acid will burn you if it's not in your stomach. So if you get sick and you throw up, try to throw up in the sink and not on somebody, because it'll burn them. We're not going to be dealing with glass where you have to push it into a cork or anything like that. But if you do in the future, if you need to force glass tubing into a cork, the glass needs to be smooth on the end. So you fire polish it. You'd have to learn that too. And you lubricate it with a little bit of water. And then you grab it down as close to the cork as possible. If you grab it out here on the end, then there's a potential to be off center and you could snap it. So you grab it close to the cork and you push a little at a time. How about breathing stuff, detecting odors? You take the test tube with a beaker and put it right up in your face. No. You do what they call wafting. You take it and you go like that, just get a little bit. Some things it takes a high concentration before you can smell them. Others, just a little bit and you can smell them. That's what the odor is. The danger is at what concentration do you experience respiratory distress? And sometimes the concentration that will distress you in your lungs and your breathing, your trachea, is much, much less than the detection odor. So you always have to consider that. And I try to design the experiment so that's not an issue, but for future reference. And then you have these placards, right? I don't think we have any placards around here, do we? Maybe on the door. That describe hazards. It's kind of like a square tilted 45 degrees. The top one is for flammability, the left one is for health, and then the one on the right is for reactivity. The one on the bottom is for special information, whatever that may be. Anybody ever read a material safety data sheet? That's how you find out what possible hazards there are. There's a whole book of them right back over there against that wall. It's a black binder with red letters on the side. That's where you go to find out whether there's a hazard. And this is an example of I think in material safety data sheet, I think they just say safety data sheet now. Yep. The lab? Oh, okay. This is a face-to-face course. So ideal, submit hard copies. But if you say leave your hard copy at home, or you are absent the day you're supposed to turn it in, then that's another option. But you don't have to do both, right? Turn it in hard copy, you're done. But you can submit it online. Let's see. Okay. So you've also got some instructions here on what to do for chemical spills, large area, small area in the eyes. I don't think anybody's going to ingest chemicals. Burns, right? What do you do at home if you burn yourself on a hot item?
Well, I also don't get mustard.
I wouldn't want to do that first. First you cool it. Yeah. You cool it as fast as possible. That limits the extent of the damage. And then it depends on how severe the burn is, right? If it's 3rd degree, you want to go to the hospital, right? If it's 1st degree, you can usually get away with that because most people have had 1st degree burns going to the beach. At home, how do you put out a grease fire? You grab the pan of burning grease and you go over to the sink, right? No, no, you smother it. You cover it with a lid, or if you don't have a lid for it, grab your baking soda. And what are 3 things required? The fire triangle, have you ever seen that? 3 things required for a flame to be sustained. You need fuel, you need heat, and you need air or oxygen. If you cut any one of those off, you stop the fire. Get rid of the fuel, which is kind of hard to do sometimes. Get rid of the air, smother it, or you get rid of the heat, cool it down. Some fire extinguishers do 2 or 3 of those. Right? A carbon dioxide extinguisher does 2 things. Carbon dioxide is cold. It will cool it down and smother it. We have ABCs over here. They work on almost everything. So they will, and they're primarily made of powdered phosphates chemicals, ammonium phosphate, I think, mostly. When you use one of these fire extinguishers, if it's been sitting on the wall for a while, that stuff is going to be settled in the bottom. So before you pull the pin and pull the trigger, turn it upside down a couple of times, if you've got the time. In fact, that's what we should be doing every week or 2. We ought to take those fire extinguishers and just mix them up again, so they'll be ready. Okay, we talked about stop, drop, and roll. Safety information. Where's the shower? Right. Yeah. Okay. So in order to put it in this format, I've got this arrow on that table facing north. That's north. Okay. So this would be the northwest corner of the room, would be the shower. Fire exits, northwest corner, southwest corner. Right. I don't know when it started, but OSHA says that all lab spaces have to have 2 exits. And fortunately, this one does. Actually, this one has 3 exits. If you go through the prep room, there's an exit door there too. So we've got plenty of them. I might add, another OSHA rule is that all paths of egress have to have at least 2 feet of free egress. So if you drop your bag down, don't put it in a exit space. Let's see. Yeah, that's 2 feet. We're good there. We're good here. Okay. Back to this fire exits. Eye wash fountains, northwest corner. Fire extinguisher, west wall, I would say. First aid station and northwest wall. Fire blanket, west wall again. Material safety data sheets. Northeast bench. It's over there in the corner by that barometer that doesn't work. That wooden thing. Nearest telephone. Well, it used to be over there. Now it's on the speaker's podium. And then numbers. These numbers are kind of dated. I'm not sure if they're good anymore. I've got a fire number, a poison center, and a police number. Does anybody have current numbers for them? I used to have, occasionally I'd have EMTs in my class, and they'd be able to tell me just like that. But I'll give you these numbers anyway. They're all 304 area codes. Fire is 752-3601. Of course, when in doubt, what do you do? 911, right? What was that movie? I forget what movie it was. It had Tim Allen in it. You know Tim Allen from the Tool Guy, Home Improvement. Yeah. He asked, what did he ask his little boy? He says, "You know how to dial 911?" Poison Center 831-1101. And police 792-8590. Okay. Then we got the chemistry lab safety agreement in the back. You haven't turned that in yet, have you? No. Okay. So turn that in no later than next week. It's got your signature, course number, laboratory locker number. You don't have one yet. We haven't assigned buckets yet. We'll do that later. So you can leave that one blank. There's a place for my signature. Lab section, there's only one section. Right. I have, when I was a student, I had labs, courses where we had several sections of lab because the lecture was so huge, like 100 students. So we'd split them into 20 each. So we had 4 or 5 sections. Room number. What's this room number? Yeah. A234. This is building A. And then the date. Okay. So you got a lab quiz here. The interesting part is that last one, where they talk about Sarah walked into a laboratory and did this and did that. You're looking for things that she did wrong. And I've got a list of 9 of them. That's why there's 9 points there. All right, so see if you can find 9 of them. Number 6 has asked for 3 steps to take that will sharply reduce the number of laboratory accidents. I've got 4 points there because they're more than 3. Yeah, 3 will get you all 4 points, but it's okay if you add extras. And if you read the rest of the document, you should be able to get answers to the other questions readily. Like if a chemical splashes in your eyes, what do you do? So for this, it's fairly easy. It's easy to get 100% on this one. Take your time and read and think. All right. Has anybody had to draw graphs in a math class? Okay, so you understand something about the Cartesian system. Cartesian system is built in 2 dimensions on a flat surface. And it can be represented by 2 lines like that with 4 quadrants. This is the x-axis, that's the y-axis. This is called the abscissa. I always have trouble spelling that word. And this is the ordinate. On this axis, all these values on this side are positives. All the values on this side are negatives. On the ordinate, these are all positives, and these are all negatives down here. So if you're given a set of coordinates, an XY value, and you plot it here, then if they're both positive, it's going to be in this quadrant. Right? If the first one's positive and the second one's negative, it'd be over here, both negative here, and negative positive over here. Positive, negative over here. Most of the time in the sciences, we spend in this quadrant. Sometimes we bleed over into that quadrant. And I think one of the exercises in here, the graphs you have to draw, does go past that into this quadrant over here. Has anybody attempted it yet? No? Okay. So if we plot a pair of numbers, an X and Y numbers, it's going to go up here somewhere. And sometimes in some math classes, they'll say, all right, you put the value there and the value Y, XY value for that. Now, if we have a list, if we have a whole bunch of those number pairs to plot, we might have them in a table first. We might have X values here and Y values here. And they're paired by this one with that one and that one and that one. So each one of these would be an XY pair, and you'd plot them on your graph. So what if you're given data and it doesn't say which one's X and which one's Y? How do you know? Well, in the sciences, by convention, the X is always the independent variable. And the Y is always the dependent variable. So what do we mean by that? In an experiment, you may be, as the experimenter, you may be adjusting the independent variable and watching the outcome as a dependent variable. For instance, if we have a trapped gas and we adjust the pressure and say, what does it do to the volume? How are they related, pressure and volume? Well, if I'm in control of the pressure and say, what does it do to the volume? Then the pressure is the independent variable. And we would plot it like this: pressure here, volume there. Right? If, on the other hand, I squeeze the gas, I change the volume, then the volume would be the independent and the pressure would be the dependent. Then we plot them the other way. So you have to read the experiment and say, what's being done? Who's doing the changing? If the experimenter changes that variable, that's the independent variable. Okay. What's next? Okay. The first example here in figure 2 is a relationship of temperature to volume of a gas. Let's see, temperature to volume. Let me remove some of this fluff. Okay. Temperature to volume. If temperature is on this axis, and by the way, if you need to draw a graph and all of your data points are positive positives, X, Y, positive, positive, you only need to draw this part of the graph. You don't have to draw the rest of it. Okay. In this case, we're looking at temperature on this scale and volume on this scale. And by the way, we're labeling it such that the units of measure are Kelvin. And here the units are liters. Okay. And then we have a title up here also. First rule, when you draw a graph, the graph must stand alone. Everything you need to interpret the graph should be there. So you need a title, you need what the axis represents, the units of measure on the axis, and then, right, the markings and how much each mark represents. Numbers on the marking. They're called tick marks. And then you can put extra stuff, but that minimum. So in this case, when they draw temperature versus volume, as temperature goes up, volume goes up. So you could say you got a point there, point there, point there, point there, maybe like that. Right. So you plotted all your temperature volume pairs, and there they are. So that's kind of a mess, isn't it? So if we want to make some sense out of it, we need to draw a line that is roughly representative of that relationship. And it looks like a straight line would do the best. So if we do a best fit line, it's probably going to be like here, from here up to here. Okay, that would be the best fit line for that data. How do we know it's a best fit? Because the difference between each of these points and the line itself is minimized. So I wouldn't draw a line over here, I wouldn't draw a line over there, because that would make the deviations too large. You want to minimize the deviations for all your points with the line. That's a best fit line. Now, suppose we want to use this graph and interpret it for at what temperature would the volume be here? Right. Well, there's no point there. So that's why the best fit line is there. So we draw it out to the line and then we drop down. At that temperature, you should get that volume based on that line. That's called interpolation. When you're inside your data points and you're picking out data pairs that are not in the set, but they're on the best fit line. That's interpolation. Occasionally, we want to go beyond the line. Just keep extending the line. Anything out here or up there is extrapolation. Right? You have to be real careful with extrapolation because you have no data points to support what you're assuming. You're assuming that the line is straight on either end. But for all you know, it could go like this, or it could go like that, or like that. You don't know. So you have to be careful with using extrapolation. Interpolation is much simpler, right? You have evidence for these values being useful. But outside, the extrapolation is risky. Okay. The title for your graph should say what the graph is trying to represent. Just say, you could just say comparison of volume in response to change in temperature. And that would be a title for the graph. Now, if you have a straight line, straight lines are nice. I mean, they're good. Scientists love straight lines because they're so well behaved, right? We know how to identify a straight line with a formula, a mathematical formula, right? Y equals mx plus b. There's the slope of the line, and there's the y-intercept. So if we extrapolate this line down here, there's the y-intercept. What's the slope? Remember? Rise divided by run. So the rise would be, say, if you go from here to here, the rise would be a change in y from there to there, based on here, there to there. And the run would be a change in x from here to here. Okay? Rise over run. That's the slope of the line. If the slope is positive, it slopes up and away. If it's negative, just the opposite. Okay, so the sign of the slope tells you which way the curve or the line is sloping. Positive, negative. Now, in your data sets, if you're asked to calculate the slope of a line, and you've plotted your line, you plotted your data points, and you're drawing your best fit line, if the best fit line actually falls where you have a data point here and a data point here that are actually right on or very close to the line, you can go ahead and use those values to calculate the slope. Otherwise, you've got to pick a point here and a point here, and then read the difference in y and the difference in x to calculate your slope. All right. Okay. Now, once you've got the slope of the line, that doesn't describe the whole line. You got the slope. How do you get the y-intercept? Well, if you got those 2 points on the line, you've got an x and a y value, right? You put in the x and you put in the y and you put in the slope, solve for your unknown. That's your y-intercept. If you don't have values here, then take the ones that you use to calculate the slope, just one of them. Say, I figured this one was x, y, so put those values in with the slope, solve for b. Okay? Anytime you've got an equation and there's only one unknown left, you can solve it. Let's see. Then there's always the possibility for nonlinear relationships. All right, so let's make some room here. And I think the one that they're going to use as an example, let me see if that's true. Yeah. Pressure and volume. Pressure versus volume of the gas. Pressure usually in the atmospheres for our purposes. So plot the values, and this is Boyle's law. We haven't come to the gas laws yet, but when we get to Boyle's law, pressure times volume equals a constant value always. So if pressure goes up, what has to happen to the volume? It goes down in order to retain that constant. Okay, so when you plot it, what does it look like? Well, there's a graph here. Figure 3 on page 19. The top one is a plot of pressure times volume. And you get these data points, and your best fit curve is like that. Right? So whenever you have this relationship and you plot it, it always produces a particular type of curve. It's called a hyperbola. Everybody remember a hyperbola from math class? No. Characteristic of a hyperbola. Now you can have hyperbolas anywhere on this graph, but for our purposes, we're going to stay in this quadrant. And if you keep extending the line out here, whether the data points or not, whether you extrapolate or not, this line will never touch that axis. And this line will never touch that axis, ever. That's characteristic of a hyperbola. It makes sense. What is the volume value if this touches that axis? 0. If this ever gets to that axis, you're right there. The origin is 0, 0. So volume is 0, right? If that happens, 0 times P is 0, isn't it? It won't be your constant value anymore. Right? So if you get really, really close to that axis, volume it could be a really small number, like 0.000023. But that means P has to be huge. Right? So anytime you have this relationship, it's always a hyperbola. But remember, I said scientists don't like curves. So we want to make a straight line out of it. How do you make a straight line out of this data set? Without violating any laws of physics or math? Well, suppose I can divide both sides of this equation by the same value, correct? And I'm still kosher. Right? Let's divide both sides by V. Right? I can do that. That means this V cancels. And now we have P equals K over V. I don't like it that way. K is a constant, right? My variables are P and V. So what if I say this? I factor out the K and keep this one as a separate factor. So what does that look like? That looks like Y equals MX plus B. Okay, so the X, that puts 1 over V down here. So we should plot it 1 over V over here. And if you do, you'll get the same result. But what does that make K? The constant is the slope of the line. And what's B? How do we get B out of that? Well, remember, if you have Y equals MX plus B, and there's no value given for B, B is equal to 0, which means the Y-intercept for this transformation is 0. So the transformed line is going to be like that. If we change this to that. And remember, anything you do through the number, you do it to the unit of measure too. So if we take the inverse of V, we have to take the inverse of the unit of measure. Right? L to the minus 1. Liters to the minus 1 is the unit of measure. Now we have a straight line. All right. I don't think we don't get into figure 4. I will to call your attention to when you start answering questions in the back, there's a required section that goes for 1 page, 2 pages, 3 pages, 4 pages. And in those 4 pages, you have 3 graphs. You have temperature volume, you have pressure volume, and you have pressure 1/over volume. Those 3 graphs will satisfy the required section. Then there's a bonus section, and you can take it or leave it. Right? If you want to tackle it, fine. It doesn't matter. All right, so let's talk about how to graph your data. You're going to be doing it by hand. Let's get rid of this. And you'll see the graph paper that's built into the procedure. It's on the last pages, I think. Back there somewhere. Not on that copy, that's a key. Here it is. So you've got graph paper. And you'll notice that that graph paper can either be held up like this, or you can turn it like that. That's portrait, that's landscape. That's one of your first decisions. Where do you want to plot your data in a portrait scale or a landscape? You want to turn it on its side. So how do you know to do that? It all has to do with how much information you need on each axis. The axis that needs the broadest numbers will go on the longer axis. Right? If that happens to be a dependent variable, then portrait will get it, because your dependent variable would be the tallest one. And then the shortest one would be like this. But if it's the other way around, if your independent variable needs more, then you go down here. So you need portrait, landscape, portrait versus landscape. Then you've got to decide which axis is which. You know, axis independent, dependent. And you're doing those at the same time, actually. Then once you've decided that, then you say the data range for each axis. How are you going to lay out the data range? Let's say we've decided to do it landscape. Right? So you'll notice on that paper you have major dark lines like this going all the way up and then all the way this way. And then in between, you have fainter lines, majors and minors. I don't think so. Oh, it might be
Computer lab?
might be physics.
Yeah, right.
It's right next door, right here. So you decide that you've got a number from here to here. And if you say each one of these is worth, say, 10, 20, and you've got 150 in that x-axis column from 0 to 150, then 150 is going to be out here somewhere. So I say, oh, I can't do that because I won't be able to plot all my data. So you chop it in half and shrink it back until you get the highest number down here. The idea is to maximize the use of space. You don't want to set up your axes here, here, and here so that you're drawing your whole graph right in here. That's just dumb because you can't use it, right? You have to get a microscope or a spyglass and get down here and say, okay, if I want to read off that graph, I got to look down here and see. You want to spread it out as much as possible. So that requires knowledge of the data range. And then when you know the data range, you want to set up what are your tick marks, right? Major and minor. The major tick marks are determined by how can you use the most of your space. And in fact, if this is the paper, you're going to have your graph's going to be in here like that. So then you would have, say, a major tick mark. Notice that those dark lines, between the dark lines are 5 spaces. So if each one of the dark lines is 1s, 1, 2, 3, 4, then each of the light lines would be 0.2, 0.4, 0.6. That's a little difficult to read. What if you go 2 dark marks? Say go 2 marks is 1. Now you have 10 light marks in between. That's a 10th. So each one is 0.1, 0.2, 0.3. That's easier to read. Okay. Once you've got your tick marks laid out and labeled them on both, then you should cover as much of this graph as possible with your line or your data points. Okay. Then, like I said before, you're going to need to have axis labels, label the axis, and units for each one. And you're going to have your data points in here, and you're going to have a best fit line, and you're going to have a title. Okay. Then, if you draw it as big as possible, and you take account of those major and minor tick marks so that you can read them easily, then you can use your graph to answer the questions by just looking at your graph, following the lines, and interpolate. Okay. I'll say a word about the extra credits. The first one is plotting on this axis the volume of base, and on this axis is the pH. So what you're going to get from that, when you plot those values in that first bonus section, you're going to get a sigmoid curve. That's characteristic of titrations. But you still follow these same rules in order to get the maximum use, right? Oh, let's go back to the first graph that you're going to grow, temperature and volume. Yeah, notice that in this case, the researcher is changing the temperature. That's the independent variable. And the response is the volume, dependent variable. Notice that you're going from -50 to 100. So in that case, you're going to have, instead of the y-axis being here, you're going to have a y-axis here, because this is always 0, 0. So you're going to have negative values out here, positive values out here for temperature. Okay. And then the positive values are the response of volume. Okay, back to the bonus. So that's the way the first one will look. And the second one. The second one is what's called a broken curve. Time versus temperature. So you can plot, like I said, you don't have to do these, but you can plot time here and temperature here, I think. Yeah. And this reaction that's described will have points here like that, and then all of a sudden it'll go like that. That's a broken curve. So you would draw your best fit curve there and your best fit curve there. And then to answer the question, one of the questions is, what's the difference in these temperatures? Well, if this one occurs here and that one occurs over there, they don't overlap in here. So what you have to do is extrapolate here and extrapolate there, and then you can measure the change in temperature. Okay, any questions?